My name's Reese Kilburger Stumpf, and I make wine in my closet oftentimes. So I would like to use this final project as an opportunity to do some research and hopefully make the ways I do that a little more precise. So the topics we're going to cover today, we're going to cover some of the background needed for this project, the setup of the experiment. I collected the data myself, the numerical computation methods I used, and we're going to talk about what they were, how I think they did, why I chose them, and we're going to go look at the results, which hopefully I will use very soon. So some background. So to make wine, all you need is to put yeast into fruit juice, give it time. Generally, that'll give you wine. You let it sit for a month, you'll get wine. Now, what's happening under the surface there is the yeast is metabolizing the sugar in the fruit juice, and basically it poops out alcohol and farts CO2. So that explains why the bubbles are there in that glass of cider I made a couple months ago. That's natural carbonation. That's why beer and champagnes are carbonated. So one thing that's a little different though, it's not quite that simple. So you would not be very healthy. I would not be very healthy. I would not feel very good if I was just eating sugar constantly. I would be stressed. My body would be stressed. I would produce things that were not good for anybody. Yeast do that too, right? So if all they have to eat is just sugar, they're gonna be very stressed. Their bodies are stressed, not bodies, but they're stressed. So that produces off flavors in whatever beverage you're making. And it really just isn't good sulfury. It gets sharp, nasty stuff. One way you can limit that is to reduce stress on the yeast by providing them all the micro and macronutrients they need. So you can buy things like yeast nutrient for a couple bucks. It's a big bag of powder, and it's things like phosphate. It's things like yeast available nitrogen. Just other compounds that they need for a healthy metabolic life. So that's kind of what I'm going to investigate here is when to add those nutrients if I'm making a high gravity beverage like wine. It matters less in like a beer or a cider because there's not that much sugar to start out with. So the yeast just aren't going to be as stressed. There's less alcohol present. There's less sugar present. So they're just not going to be as stressed. But if you have something you're making a wine, you start out with a lot of sugar. A lot of sugar means more alcohol at the end. So with a wine, you're starting with a lot of sugar, and that means you need a lot of nutrients to help out the yeast. So some of the terms I'm going to be using are specific gravity. So the specific gravity is just another term for how much sugar is present or how much of a solute is present in a solution. So it's like a percentage of how much of the solution, in this case, is sugar. And it's on a scale of about 1 to 1.1 ish. You can go higher than that, you can go lower. Generally, it's that. Water is 1.000 in theory. I think that's how it's defined. The scale is defined like a soda or like a juice or something. Maybe starts out at about 1.05. And that's like about as sweet as it is pleasant. It's about as sweet as you want to drink something. I started out for this with a sugar solution that was 1.1, which is way too sweet to drink. It's not tasty. Yeast like it though. So that'll give you a wine. 1.1 will give you a wine that's about 14% is about what I ended up with. So a sugar break is just when you get that specific gravity at a particular percentage. So the ones I'm investigating are 1/3 sugar break and 2/3 sugar break. So the 1/3 sugar break is when 1/3 of the sugar you start out with is gone. So you start out with X amount of sugar, X over 3 of that sugar has been metabolized into alcohol. It's gone. So I'm looking at the 1/3 and the 2/3 sugar break. When 1/3 is gone and 2/3 are gone, and that just creates a very even schedule. So typically that's when you would add nutrient is add a sugar break. You don't want to add all the nutrient all at once because it'll overwhelm the yeast and stress them out. So you want to add nutrient at those sugar breaks and at the beginning. So what we use to measure this gravity to get this data is something called a hydrometer. And I'll go more into detail about the measuring process later, but this is a hydrometer. It floats, it's weighted to float at a specific height based on the density of the sugar in a solution. And you can see there's measurements on there. There's all sorts of markings that mean all sorts of different things. But that's the main tool I used. So I want to get an approximation for these sugar breaks based on time, because the measurement process, as we'll see soon, is invasive and it can introduce contaminants into a wine that are not good as it ages. So I want to get an approximation for how long it takes to get to the 1/3 sugar break, the 2/3 sugar break. So I can just look at how many hours it's been since I started, and I can just add my nutrient and I don't have to take any measurements. So the experiment, as I started 2 fermentations, and each of those consisted of about a half gallon of juice and enough sugar to bring the gravity up to 1.1, just white table sugar. And I mixed the two juices together into one container, added the sugar there, and then split it up again just for continuity's sake to make sure that the two had identical conditions as close as I could get. And about 5 grams of yeast nutrient just to get it started, just so the yeast didn't have any problems getting started because I had really limited time to do this once. And then a yeast slurry from one colony of yeast from a fermentation I'd done. It started as bread yeast, and then I used it to make a cider, and I saved the yeast, so it's the same colony, so hopefully those conditions are as similar as they can be. So what I did is I started one half gallon, I waited about 4 hours, and then I started my next half gallon. And in that time, the yeast, I'd taken them out of the fridge, put them in some water to hydrate again, and they'd warmed up and started blooming in those 4 hours. So that you'll see the fermentation rates are dramatically different. So it ended up being a sort of a comparison also between warmed yeast, like rehydrated yeast, and just cold yeast straight out the fridge. So what I had those two set up, and I measured the gravity every 8 hours. So that gravity measurement process is about as follows. So this is pretend it's my fermenting wine. So I've got a little test cylinder here. It's just a cylinder that's about big enough for the hydrometer that I showed you. So this is a regular turkey baster. These are all, I would have had to sanitize all of these before starting. Then you don't want to pour the wine because there's all sorts of yeast just at the bottom, and you don't want to really mix it around too much. You want to kind of let it sit. So the turkey baster is the least invasive way you can do that possible. So you set it down, you let the hydrometer find its equilibrium, and then you can read the gravity off of these markings on the side. So that's the process, 3 times a day, every 8 hours for about 10 days. So I ended up with about 60 data points, 30 per bottle of wine. And that was a week and a half of my life. It was unfortunate. So we got those, all the data together into a CSV, and now we're ready to do our math on it. So my first goal is to turn these discrete data points into a sort of a function. So I need to interpolate between them. So I chose cubic splines for a number of reasons. I want a method that is stable. I want the derivative to be easy to take because I want to find a root later on with Newton's method. And linear, and I want it to approximate as well as it possibly can, this curve. So linear approximation would be okay. It just wouldn't approximate the curve in the way that I would want it to, I don't think. It didn't look like it when I tested it. And Lagrange polynomials interpolation was also an option. I didn't use that either because it would return a polynomial of degree 30 for each interpolating curve, which is just far too unstable. It was far too unstable when I tested it. And the derivative is difficult to find and also unstable. So it just made way more sense to go with the cubic splines here. And you can see these splines in that graph on the right. Those are the splines for bottle A is the one that started with the cold yeast, so you can see it took longer to start fermenting, and bottle B is the one with the warmed up yeast after about 4 hours. It was room temperature. That got started way quicker because yeast were already blooming, an active colony. They were not dormant anymore. That was a lot quicker. So there's my spline. So and then in order to get my sugar breaks, I figured the best way to do that was to use a root finding function. So I needed to shift the spline, so I constructed 4 shifted splines, two per bottle. I shifted the splines by the amount of sugar that's at that sugar break, right? So I had that calculated in the program. It calculated the amount of sugar present at the 1/3 and 2/3 sugar breaks, and then I had to shift the splines accordingly. And then we can do a standard Newton's root finding method. Now I had to play around with the initial guess here a little bit. It was returning really weird results if the initial guess wasn't ballpark. But good thing I had these plots here, so I could just kind of ballpark it, and it improved very quickly. So I ended up with initial guesses of 20 for the first sugar break and the 50 for the second sugar break. That's in hours. So the results. So you can read those exact sugar breaks. Realistically, for me, this means if I take the yeast out of the fridge, throw it in my ferment, and let it go, I want to add some yeast nutrients 1 day after the pitch and 3 days after pitching the yeast, basically to the hour, as close as I can get, because that's about 1 in 3 days if you see there for the cold yeast. That's a lot quicker than I thought. I used to think it was about 4 or 5 days for the second, I used to think about 4 or 5 days until I wanted to add yeast. At that point, as we can see here, it's basically too late. Like the yeast have done their fermentation. If they're going to be stressed, they're stressed. The off flavors are in there. So that means I need to add a lot quicker. And especially if I give the yeast time to hydrate before pitching them, then I really need to get on it. That's just under a day and about 2 days after. So the reason I'm sort of flying so fast and loose with the precision is I think the precision is not particularly high. It's not nearly as high as the decimals on these approximations suggest. And that's for a number of reasons. One, I mean, you saw in the measurement, the hydrometer isn't very precise. I'm reading like 2 digits of precision off of a floating scale that might be calibrated for a different temperature. It's good enough for me. But then we start to add on, now I'm approximating with a cubic spline, which it probably would have been better to do an exponential fit, but this is not a stats class, to get a smoother function, because you can see the cubic spline is pretty wonky in there. It's almost like a step function at times, due in large part to the imprecision of the measuring tool. And then on top of all of those, we've stacked another Newton's method approximation. And that's probably the most accurate thing here, but it's taking in, questionable quality data, questionably precise data. So I'm not that worried about the exact precision. I just wanted a ballpark. So I've applied the numerical methods as well as I can, and I have new data that I'm going to hopefully use to make a mead here in the coming week if I can get some honey. All right, thank you for your time.